minute is not a big deal. Okay, so let us start officially. So again, welcome to physics 405, mathematical physics. Uh, and I'm seeing some weird blur. I think it's a driver issue. Yeah, so I might need to reinstall the driver. So welcome to this course that is titled as Mathematical Physics. So our goal is something like this. At first, we'll try to look at some path integral formulations, both in quantum mechanics, and if possible, we'll try to see some quantum field theory as well. But no knowledge of quantum field theory will be necessary. The main idea is to grasp how to use these path integrals to, compute some quantities of interest. So path integrals. And after we are done with path integrals, I would like to introduce some very fundamental concept, that is like mapping, what are sets, um, what is a topological space. So I like to call this some background material involving some point set topology as well. And then I would like to move on to the homotopy and homology groups. If you're doing an algebraic topology course, I think you are already taking some steps to study these things, but we'll try to study them from a physicist's point of view in this course. And this should be our main priority. This should be, the takeaway from this course. Even if you um, think that, okay, the contents are really overwhelming and there is only one thing you want to focus on, this is the thing that you should focus on for this course. And we'll spend some time on these things. And after that, we'll try to go on to manifold theory and we'll try to see how far we can cover. I have an intention to cover complex manifolds as well, but we'll see. It will depend on how much time we have and how fast we can go. Okay, so I think I wrote it on page 11. Wow, great. So I need to rearrange the PDF. So today what we want to do, we want to take a first step um, towards path integral formulation, and we want to start by discussing some functional calculus. So everyone is familiar with a single variable or multivariable calculus where you do some certain operations on functions, and it might be integration, differentiation, or Taylor expansion and stuff. We'll try to see those things, but this time we're going to deal with some function nulls. So the first question that comes to mind is that what is a function null? Well, to understand that, we first need to introduce the idea of a function space itself. Oh, and do I need to show you something, that is the notation and conventions that I'm going to use in this course? Should I mention that?
I think that would be good.
Okay, so notations and conventions. I'll explain them as we go as well. So even if you forget it, don't worry about it. So we work in natural units. That means h bar equals to g equals to k. K is the Boltzmann constant, is equals to c, which is the speed of light. All of them are equal to 1. for us, okay? And throughout this course, we'll use the Einstein summation convention. That is, let's say you have something like this, xi, xi. This means x1 plus x2 plus x3 da 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 plus xn x sub n, where I ranges from 1 to n, something like this. Okay, so this is just a summation convention. You see the same index in the superscript, same index in the subscript. It's just a sum over all the things. And even though this is the standard, some authors also uses the summation convention like this. I think if you have done some linear algebra, I think most of you did, you have seen something over there, something like this. Let's say xi, lij, x of j, right? Something like this. Here, there is a summation over the j index. We just omit the summation sign. This can be a column vector, this x's, and this L can be a matrix. So we'll try to clarify those things as well. This thing is only valid or convenient to use if you're working in a flat space-time dimensions. That means there is no intrinsic curvature. But yeah, it varies from author to author. And we'll sometimes use this one, sometimes use this one, depending on the problem that we're dealing with. So if you're confused, just ask that whether it means a summation or not. Okay.
The one with the x on as the superscript or x on the subscript, are they different?
In flat space-time dimensions, no. If your manifold is flat, or so to say the the space-time you're working with, if it's flat, then no, they're not different.
সাবস্ক্রিপ্ট দিয়ে আর সুপারস্ক্রিপ্ট দিয়ে কেন ডিফারেন্সিয়েট করা হচ্ছে এখানে, লাইক দুটোই নিচে দিচ্ছে না কেন?
Because if you think of them as, let's say for now, let's say they're column vectors, okay? And if you're familiar with the inner product, this is nothing but an inner product, right?
Yes.
An
Yes.
inner product does what? It produces something invariant. So if someone else, let's say you and your friend, you guys are measuring the same thing, there should be something invariant about it, and somehow that is related to some inner product or trace of a
বাম
measure.
দিকেরটা কাইন্ড অফ ডুয়ালের সাথে ইয়ে করার জন্য ডিফারেন্সিয়েট করা হয়েছে কি, যে ডুয়াল স্পেসে ইয়ে করার জন্য?
Yeah, the dual space. And if you speak in terms of tensors, then one is the covariant tensor and one is the contravariant tensor, or so to say a one form. So yeah, ওইটার জন্য হচ্ছে এরকম ডিফারেন্সিয়েট করা হয়. We'll try to see that in our tensor algebra tutorials. What are covariant stuff, what are contravariant stuff. So the idea is that this x prime. Yeah.
Question: wouldn't one of the j's be downstairs in order for it to contract? একটা j upstairs, একটা j downstairs.
Well, that's the thing I was talking about. Like when you're talking about contraction, by this notation over here, this one should be upstairs, one should be downstairs, right? But some authors write it like this as well.
Oh, acha.
If you are working in Cartesian space-time or Cartesian, space, so to say, then there is no there's no way to distinguish between these two, like the upstairs and the downstairs index. And what Nahi asked is that why this, right? Now, why do I have to bother with all this upstairs and downstairs? So if someone is measuring something in some prime frame and he's writing it as x prime dot x prime, and this has to be equal to some x dot x, this is what invariance means, right? Two things, two frames, but they're measuring the same thing. And for this quantity to be invariant, x superscript I has to transform the inverse way from how x downstairs transforms. লাইক বুঝতে পারছো যে এক্স আইটা হচ্ছে যে তোমার সুপারস্ক্রিপ্টে যেটা থাকে সেটা হচ্ছে তোমার এমন ওয়েতে ট্রান্সফর্ম করবে যেটা তোমার এক্স আই ডাউনস্টার্সে যেটা থাকতেছে ওটা ঠিক উল্টা হইতে। ফর এক্সাম্পল এক্স আই যদি এইভাবে ট্রান্সফর্ম করে যে এক্স ডাউনস্টার্স আই প্রাইম ইজ ইকুয়ালস টু এল এক্স আই, or it should be downstairs, then the x superscript I will transform as L inverse 1 x superscript I. Okay, so when you multiply them you can see that this equality is satisfied, and it has something to do with the how covariant and contravariant vectors, or so to say tensors, transform. Is that okay? If you're confused you should ask.
My,
So some
yeah,
of us
I'm
never
fine.
heard of.
I mean, like, will you go into details
Yeah,
as we
in
go?
the in the tensor algebra
Then
tutorial.
I think fine for now.
Okay, so these are our notations and conventions. Okay, again if you are confused you should ask. So as I was saying, to go into functionals, first we'll try to take an informal view at what are function spaces. So function space. Just like your ordinary space-time or space, function space is a space. Let's say this is our function space, which I denote with some calligraphic A. All these points in this space will be now a function. Let's say this is some point A, small a, and it represents some function. Okay, so আমাদের অর্ডিনারি স্পেস টাইমে আমরা সাধারণত যখন কাজ করি সেগুলো সাধারণত কি থাকে, একটা নাম্বার থাকে, রাইট? There is some sort of a number associated with each and every point, but here each and every point will represent a function that will take input from your space-time coordinates and produce a number. Does that make any sense?
Could you repeat that?
Yeah, so function space হচ্ছে এমন একটা স্পেস যেখানে প্রত্যেকটা এন্টিটি এক একটা ফাংশন. They're not numbers, they're functions, and what they do, those functions eat up coordinates from your space-time or whatever the space you are dealing with, and then they will produce a number. For example, f of x equals to x square. This can only produce a number if you provide a value of x, right? Which can be your space-time coordinate or something. And it can be a multivariable function as well, x1, x2, x3. And it can be, let's say, x1 squared, x2 squared, x3 squared. And if you have the value of x1, x2, and x3, then you can extract out a number from this function. So this x1, x2, x3, x1, x2, x3, they belong to some R3, a three-dimensional real space, let's say. However, this function itself, f of x1, x2, x3, this belongs to the function space. This A is our function space.
Like, for example, x to the power x1, x2, x3 একটা পয়েন্টের জন্য আমরা ডিফারেন্ট ফাংশন পাবো, তাহলে ওইটাকে কি একটা ফাংশন স্পেস বলা যাবে?
X to the power 1 times x to the power 2 times x to the power 3. If this is a function, then yeah, it will be a point in function space. Did you?
What is the
that?
dimension? What is the dimension of the function space?
Infinite. It's an infinite dimensional vector space. Because if you come to think of it, your entities, that means the functions, they are made of these x's, right? And how many x can you take? A lot of them. So these are infinite dimensional vector spaces. Yeah. আচ্ছা নাহি, তুমি যেটা বলছিলা মানে x1 to the power x2 to the power x3, ওইটা কি ফাংশন স্পেসে বিলং করবে কিনা, দ্যাট ওয়াজ ইউর কোয়েশ্চেন, রাইট? করবে।
মানে আমি যেটা
করবে না কেন?
বলছিলাম যে
Function.
R3 এর একটা পয়েন্ট নিলাম, R3 এর একটা পয়েন্ট নিলাম, সেটা হচ্ছে আমাদের একজন একটা ইনস্টেড অফ আ নাম্বার একটা ফাংশন স্পিড করবে আর কি। So,
Let's say 2 to the power x to the power 1, right?
বা x টু দি পাওয়ার
Something like
লেটস সে ওয়ান ডিমেনশনাল ইয়ে থেকে যদি করি যে মানে y যদি ভ্যারিয়েবল হয় তো y টু দি x, তো x হচ্ছে r1 একটা পয়েন্ট বা এরকম। সো
Well,
তখন
x আর y গুলো
x
তো
এর একটা
ultimately
পার্টিকুলার
R1 এ
ভ্যালুর
belong, মানে
জন্য
R, well, not R1, not R1, R2, because x and y, so they should belong in R2. And if you take points from R2 and you put that in your function, you get a number again, right? So that's a mapping from R2 to R1. That won't belong in the function space. But if you say, J, okay, I have these x and y's in my R2, but I want to write a function f of xy which is equals to y to the power x. That y to the power x will belong to the function space. Okay,
Okay.
clear হয়েছে?
ফাংশন স্পেসের জন্য কি কোনো স্পেসিফিক লাইক অ্যাক্সিওমস লাগবে নাকি জাস্ট একটা ফাংশন আর ওই রিয়েল
Well,
ফিল্ড আর
for our
axiom
course, no.
লাগবে?
For
Oh, I
our
see.
course, no. So these
Oh,
are topics in functional analysis. Huh?
Mhm.
That's a very rigorous course if you want to do it any day.
No.
But for our purpose, no.
I see. Okay.
Okay. Yeah, I mean, maybe there is something, but we'll not focus on that. We are rather interested in what we can do with this construction. So this is your function space. And now we can try to define a function null. So let's get into the definition of a function null. You have seen functionals already. So what is a function null? A functional is a mapping that takes a function as an input and generates a number. That's pretty much it. So if I write it down, it is a mapping that takes a function as an input and generates a number. And by number, I mean scalar. Okay. So how can we see this? Well, let's say this is our function space again, A. And there is some sort of a mapping. Let's define the mappings with something like this. F of capital F of x. This is how we write function nulls, with third bracket, and inside the third bracket the argument should be function. So you are seeing some sort of an analogy here with the ordinary calculus that you do. In ordinary calculus, what you do, you take a function and in the argument you have your x, y, z, whatever, right? And in terms of functionals, the arguments are functions itself. It takes some input from the function space and it maps it to some scalar. Let's say for এটা ক্লোজ হয়ে গেছে পুরোপুরি, but I think it would be fine. So are you guys seeing this weird glitch? Like there is this green,
No, it
sort of
looks fine
particles
for
in the.
me.
I don't know. I'm seeing this.
না
I
কিছু
don't know.
নাই।
No. Not
Maybe I'm
It's monitor.
experiencing. No, I don't think it's the monitor. Maybe I'm experiencing a glitch in the matrix. And let me take a picture of it because otherwise people won't believe it. Ask Rakin about this in his matrix theory class.
all right.
Yeah, so as I was saying, so what your functional does is that it takes a function and it maps it to, okay, now this is inconvenient. was it? Yeah. And it maps the function to a real number or a complex number. So in general, you can just write it maps the function to a complex number. Okay, any complex number. So this is some sort of a physicist type of definition of a functional. And what I wrote here is just a map from function space to your space-time coordinates. And let me try to draw that again. So this is your function space. And let's say this is your, space where you have these numbers. Let's say 1, 2, yada, yada, yada. There might be complex numbers as well. So functional is just a map from this space, the function space, to this space. This is what functional does. Okay, it's a mapping. So can anyone tell me that whether you have seen something like this before? What might be a
For
example?
example, a curve of a line, sorry, curve length এর যে একটা ফর্মুলা আছে, so we give মানে ওই ইন্টিগ্রেশনটার মধ্যে একটা পার্টিকুলার ফাংশন বসালে আমরা একটা পার্টিকুলার লেংথ পাবো। সো ওইটা একটা ফাংশনাল হইতে পারে যে যেটা হচ্ছে যে 1 স্কয়ার রুট অফ 1 প্লাস f প্রাইম স্কয়ার। সো f এর এক একটা f ফাংশনের জন্য আমরা হচ্ছে এক একটা ভ্যালু পাবো। সো এটা হচ্ছে একটা
In other
ফাংশন থেকে
words,
একটা নাম্বার
the
নিচ্ছে।
norm of a function, basically, right?
Yeah, norm
কেন?
of a function as well.
And that's what you're taking a function and you're mapping it to a real number.
হ্যাঁ, বাট নর্ম হইতে হবে কেন? লাইক নর্ম হয়তো লাইক আই গেস ফাংশনাল একটা স্পেশাল কেস হইতে পারে, আমি জানি না নর্ম সম্পর্কে আসলে।
Okay, so let's not make our lives complicated by using the function norms. That are those are like some sort of a distance in a function space. Okay, we won't consider those things for now. But yeah, it's a good thing that you brought it up. So examples are, well, integrals, definite integrals. That's a very simple example. An integral like this, let's say minus a to b, let's say g of x dx.
Are polar to Cartesian transformation functional?
Polar to Cartesian, will that generate a number? I don't think so, because if you are considering xy going to r and theta, what you need is a transformation matrix, right?
R2 to R2 map এটা।
Yeah, this is more of a R2 to R2 map. Yeah, absolutely. So I don't think that's a function from what I know, because you are transforming your how to say this, some vector xy to r theta, and to do this transformation you need a matrix. So those are finite dimensional vector spaces. So yeah, so this is one example of a functional. If you are familiar, if you're a physics guy, I think you have seen this already. Okay, let me not write it first. Let me write something very simple. Some action. I think you have seen this, right? X dot. Maybe there is time. The principle of least action. Maybe when you started that, you have seen this, right? Yeah, this is a functional as well. And oh, one more thing. If we don't specify any limits in this course, usually what we mean is that the integration is from minus infinity to plus infinity. Okay, so this is, we are lazy, we don't want to write everything down, we want to save our time and stuff. So this is another convention, and again, if you don't get it, just ask me. So what can be an example of this action? Well, the action of a harmonic oscillator, you write the Lagrangian as what? T minus v, kinetic energy minus potential energy. So the kinetic energy is what? Can anyone tell me? What is the kinetic energy of a harmonic oscillator?
So as a function of time it will be
Anything, just
right, say cosine square theta
Why are you going to cosine square theta? No need for that. You just
আচ্ছা,
write mb square, right? The very simple
right.
thing you learn. Or so to say mx dot squared, where x dot means the time derivative, minus 1/2 of m omega square x square dt, right? And now I can show you another example that involves the integral. Let's say this is dd of x 1/2 of some phi this might seem a bit weird. This is also a functional, but here this phi will be a field, and we'll see these things in when we actually do the path integral thing. So these functional stuff are just a background material to do this path integral stuffs. So what is a field? Well, in simple terms, a field is something that has some specific value. Let's say if it's a scalar field for now, okay? And scalar field for every point in your region of interest, it should yield a value. Temperature field is an example. Let's say you have a room, you see the temperature at every point, you get some value, right? So this phi is like a field. And what are these weird things? Well, they're just derivatives like this. And why this upstairs downstairs? Again, if the spacetime is not Cartesian, then we have to make these distinctions, and we'll get back to that in the tutorial classes. Why do we do what we do? And it has something to do with the metric tensor. So this is a shorthand notation for your derivatives. This is written like this, and this one will be written like this.
বাম দিকে নিচে লিখলে ডান দিকে উপরে লিখে কেন, মানে উল্টা হয়ে গেছে?
Yeah, this is a
Confusing.
it's a confusing notation. Okay, like the down goes up and up goes down. Yeah, it was
নেমোনিকটা হচ্ছে
confusing.
যে ডিনোমিনেটরে থাকলে ওটা ফ্লিপ হবে, আমি এটা শুনছি।
Like, yeah, that's why I said like down goes up and up goes down. Okay, it seems silly, but yeah, that's how people write it. I don't know why. So yeah, so these are examples of your functionals and stuff. And this dd of x means it's a d-dimensional system. So this integration measure actually consists of dx1, dx2, dx3, dx of d. If it were a three-dimensional thing, most of you maybe write it like this, dx dy dz, but it can also be written as d cube x. That's it. Saves your space and your time. So yeah, so these are pretty much it for the notations and how we can become very silly with notations and stuff. So up to this point, is everything clear?
So far, so good.
Okay, good. So let's move on. So now we know that there is some
About
Yeah.
about a question about functional. There is f of g. I mean fog function and goff function. I think.
Where
you
is
remember
fog
that.
function and goff function?
I mean function inside function. If
I think he's talking about composition of two
function.
functions.
Okay.
Are those
Composition map.
functionals? Because they are taking in a function and
They're giving
No.
out functions.
No.
So it's not
Functional
a function.
functional should take in a function, and it should input output. You should give you output of a scalar. Okay. But if you do this composition maps, they're just mapping from one point to another in the function space itself. Okay, so that's like an operation on this function space. Let's say if you do some composition, f of x, g of x, and if you do these compositions, it's just taking you to another point in the function space itself. So that's not a functional by definition.
okay, got it.
Okay. Okay. And আমার এটা glitch হয় বারবার. It's like scroll button কাজ করে না. Okay. So since now we know what is a functional and what is a function space, let's start the discussion on functional derivatives.